When we look up at the night sky, we carry an assumption with us that the universe, at its largest scales, is consistent, that the same physical rules apply in every direction. This assumption is so fundamental that much of modern cosmology depends on it. And for the most part, it holds true. But when scientists mapped the oldest light in the universe, they found a place where that assumption begins to strain. A vast patch of sky that is noticeably colder than the rest, larger than expected, deeper than predicted. This is the cosmic microwave background cold spot. The light that reveals this anomaly is not ordinary starlight. It does not come from stars, galaxies, or explosions. It comes from a time long before any of those existed. In the early universe, everything was hot, dense, and opaque. Light could not travel freely. It was constantly scattered by charged particles. Then, about 380,000 years after the universe began, conditions changed. The universe cooled enough for atoms to form. Space became transparent, and light was released. That light has been traveling ever since. As the universe expanded, the light stretched and cooled, shifting into the microwave range. Today, it fills all of space at an average temperature of 2.7 Kelvin, just 2.7 degrees above absolute zero. This radiation is known as the cosmic microwave background. It is the earliest snapshot of the universe we can observe, and one of the most precisely measured signals in all of science. Across the entire sky, temperature variations are typically only a few millionths of a degree, which is why even small deviations matter. When scientists mapped this background in detail, they expected near uniformity. Tiny temperature differences were predicted, the result of minute fluctuations in the early universe. And that expectation was largely confirmed. But one region stood apart. The cold spot spans roughly 5 degrees of the sky, about 10 times the width of the full moon. In physical terms, it corresponds to a region nearly 1.8 billion light-years across, and it is colder than its surroundings by approximately 70 microkelvins. That difference may sound insignificant, but in cosmology, what matters is not the size of the number, it is how unlikely it is. According to standard cosmological models, fluctuations of this scale and depth should be extremely rare. Statistical simulations suggest the probability of such a feature appearing by chance is less than 2%. Not impossible, but low enough to demand careful explanation. At first, scientists suspected an error: instrument noise, foreground contamination, a statistical coincidence. That skepticism was reasonable. But when a second mission, the Planck Space Observatory, mapped the sky with higher resolution and independent data, the anomaly remained. Same location, same scale, same temperature deficit. The cold spot was not an artifact, it was real. So what could produce it? One explanation looks not to the early universe itself, but to the space between us and it. As ancient light travels toward Earth, it passes through large-scale structures, clusters of galaxies, filaments of matter, and vast underdense regions known as voids. In an expanding universe, light can lose energy when crossing such voids. This effect is known as the integrated Sachs-Wolf effect. In theory, this energy loss could make part of the cosmic background appear colder. Astronomers have identified a large void in the direction of the cold spot. Estimates suggest it spans hundreds of millions of light-years,
and contains significantly fewer galaxies than average. But even when its size and depth are accounted for, the void can explain only a fraction of the observed temperature drop. The structure exists, but it is not extreme enough, which leaves an uncomfortable reality. The measurements are precise, the anomaly is real, but the explanation remains incomplete. Another possibility is more unsettling, that the cold spot is simply a rare statistical fluctuation. In an immense universe, even low-probability events must occur somewhere. This explanation requires no new physics, no hidden structures, just chance. And while it is mathematically valid, it offers little satisfaction. There are also more subtle ideas, irregularities from the earliest moments of the universe, remnants from a time when physical laws were still settling into place. These possibilities are difficult to test, and for now, they remain unresolved. Why does this matter? Because the cosmic microwave background is not just another observation. It is the foundation beneath our models of the universe. If something doesn't fit here, it matters everywhere. The cold spot does not overturn cosmology, but it exposes its limits. It reminds us that even our most successful theories are still approximations of a far larger reality. For now, the anomaly remains, a region of the sky that doesn't quite belong, measured, confirmed, unresolved. The mystery is not that the universe contains such a place. The mystery is how many others we have yet to notice. If you want to continue exploring these unanswered edges of science and space, subscribe to Beyond the Void, where we document the unexplained edges of the universe.